So up till now, the course is focused on kinematics. We sort of developed our machinery for how to use vectors, and then we've been talking about we've been working kinematics problems, right? So kinematics is the study of the motion of objects. Well, we're going to transition and start talking about forces. And how do we relate forces to motion is sort of fundamentally where we're going to start our discussion here. So we tend to think of them in terms of this question, right? So what keeps things moving? And the idea is that this is actually what Newton's first and second laws are going to explain to us is this is actually the wrong question. Instead of asking about what keeps things moving, the way we want to think about forces is what causes an object's motion to change. So what Newton recognized is that objects will continue to do what they're doing until some force acts on them to change that motion. And so that gets lumped into dynamics. So dynamics is basically the term that we call, the name that we give to the study of how forces act on an object to change its motion. So what causes an object's motion to change, we'll see in a second, is the net force acting on it. The important thing to remember is it does not take a force to keep something moving in a way that doesn't change. Forces are only needed to change an object's motion. Now the way that we tend to think about the problem, because this fits in with our experience, is if you want to slide a block across a table, let's say, well, if you let it go, the block is clearly going to slow down. So if you want to keep sliding it across the table at that same speed, keep its motion constant, you've got to keep pushing. And the idea is that the reason the block slows down, right, it's not because you need to push to keep it moving. It's the block slows down because there is already a force, in this case the force of friction, that's acting on it to change the object's motion. You are providing a second force that basically balances out the force of friction so that the object's motion doesn't change. And so this idea of when an object's motion doesn't change is best encapsulated in Newton's first law. So we tend to think of Newton's first law as objects at rest remain at rest and objects in motion remain in motion unless they're acted on by an outside force. There are a couple important details that sort of get swept under the rug here. So probably the better way to think of Newton's first law would be objects at rest remain at rest and objects in motion continue to move in a very special way, in a straight line, at a constant speed, unless they are acted on by a net external force. So part of what this tells us is if an object's just sitting there and no net external force acts on it, it's going to continue to just sit there. But if an object is moving, we said there are three ways that an object can accelerate. It can speed up, it can slow down, or it can turn. Well, what this says is if there's no net external force, then there's no acceleration because your object isn't turning, it's moving in a straight line, and it's moving at a constant speed, so it's not speeding up or slowing down. So the idea is that Newton's first law tells us three important things. One, that forces change motion. Two, that if you don't have a net force, then you're not going to have an acceleration. And if you don't have an acceleration, then your velocity is going to be constant. So that's the idea behind Newton's first law. Newton's second law, again, we tend to think of it as F equals ma. And again, let's go ahead and put in the little details that we need here. So really, Newton's second law is the net force, right? This is the summation sign. So the sum of all the forces acting on the object is equal to mass times acceleration. And again, we know that forces are vectors and we know that accelerations are vectors. So what is, again, important about Newton's second law is in some way it's the mathematical version of what we talked about in Newton's first law. If you said that there was no net force, there would be no acceleration. So sure enough, Newton's first law in some sense is buried in what we've got here with Newton's second law. So this is going to start by telling us the same thing. One is that the net force changes the motion by causing an acceleration. Two, the net force vector and the acceleration vector always point in the same direction. And again, I'll take the opportunity here to be subtle about the important word. There it is, Always, 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 every time. We're going to take advantage of that in working problems, because that means if there's an acceleration, then there is going to be a direction that we want to take advantage of in working the problem to simplify what's going to go on with the math. And then the third thing that Newton's second law tells us is that, let's say you keep the net force the same. If you increase the mass of the object, the acceleration is actually going to decrease. So what that means is that mass is a measure of an object's resistance to being accelerated. The bigger you make the more massive you make the object, the larger the net force has to be to get the same acceleration. So this is sort of fundamentally what Newton's second law is trying to tell us. Now, in terms of working problems with Newton's second law, basically, again, what we need to remember is this is a vector equation. And so a vector equation means I've got one equation per dimension. Almost all the problems that we're going to work will be two-dimensional problems. So we'll have an x equation that says the sum of the forces, sum of the x components of the forces, it's got to be equal to mass times the x component of the acceleration. Our y equation is going to tell us the sum of the y components of the forces has got to be equal to mass times the y component of the acceleration. So this means two things. One is we're going to set up one equation per coordinate axis, just like we do with any vector problem. And then the second thing is that we need to then break force vectors and acceleration vectors up into components. And we'll see that when we take advantage of the direction of the acceleration, we're going to break up the acceleration vector in a very specific way each time. And then we'll just, once we've picked our coordinate system, break up the force vectors in the way that based on our choice of coordinate system. So this is the basic structure that we're going to use in terms of working a Newton's second law problem.